We've looked at the electromagnetic spectrum and polarization of our EM waves, mainly looking at the visible wavelengths here on Earth. But what about the electromagnetic spectrum and polarization in the rest of the universe? Now, observational astronomy research is based on what we can see with our telescopes out there in the universe, and we aren't limited to the visible part of the spectrum. We observe the universe in all wavelengths. And with all of these wavelengths, we can use the polarization of these electromagnetic waves from out there at the different frequencies to help uncover some of the mysteries of our universe. Now, polarization can help us to predict solar flares. So we do this by studying the magnetic fields on the sun and gain an idea as to what is happening on the surface. So this image here is showing a solar flare that happened on the 30th of January last year, and captured by the NASA's Solar Dynamics Observatory. Polarization is also used to study supernova, exploding stars. Now we can understand, or at least try to understand, the details of the supernova explosion by using the polarization of the light coming from it. So this is the supernova remnant Cassiopeia A. Now the lines here all indicate the polarized emission. Now this emission is coming from the coal dust inside the remnant that we couldn't otherwise notice. We can even use polarization to help image other planets. Now, I mean not planets in our solar system, I mean exoplanets. So at the moment we find most of exoplanets by an indirect means. So we look at their host star. So we can't normally image a planet because the star is so bright, and with planets being so small. But the light reflected off a planet would be polarized, like in this image here, is that we have our unpolarized light coming from the host star, and out we get is polarized light reflected off of the planet. Using this technique could give astronomers the opportunity to image a planet directly instead of indirectly by looking at the star. Now we can use polarization to look at other planets, but we could also use the polarization of light to look for life on other planets. So it may not be, humanoid life or little green men, probably more like plants. But it is very likely that there would be some kind of organism that uses starlight to create energy, like here on Earth. Now this process creates circularly polarized radiation, which we haven't covered. But by looking for this circular polarization, which is very small, we could detect new forms of life on exoplanets. Polarization can tell us a lot about our universe. At the beginning of the universe there was the Big Bang. Astronomers study this by looking at the cosmic microwave background, or CMB. So here is a map of the CMB with the polarization vectors showing where the polarized emission is and what direction it is pointing in. Yep, we can even study the beginnings of the universe with polarization. So it's polarized because the radiation scattered off free electrons. And I'll show you how. So when two waves are incident on the free electron, the scattered wave is polarized perpendicular to the incident directions. Now because the two waves are of different intensities and incident perpendicular, there is a net polarization in the resulting wave. So if the radiation was of the same intensity, there would be no net polarization. So this information about the electric and magnetic fields helps astronomers understand what happened in the first few seconds of our universe. Polarization is an often forgotten attribute of electromagnetic radiation, especially by me. But you can do so many cool things with it, like looking at the sky and playing with polarized sunglasses, which is especially interesting when you should be doing an assignment. And it can show us what is out there in our universe.